Let us start this lecture with a thought process by great scientist during independence time, that is Sir Jagdish Chandra Bose, who says that true laboratory is the mind where behind illusions we uncover laws of truth. This is really a very good statement which most of Indian scientists do not believe today, but this is the truth which we must accept and work in our mind, and then of course, we can do in the physical plane also. So, let us recall what we learnt in the last lecture. In the last lecture, we initiated a discussion on non-chemical rocket engine, and which can be classified basically into three categories for our discussion. One is electrical, then solar and nuclear, and later on we also divided electrical into electrothermal, electromagnetic and electrostatic, and we discuss about the electrothermal and arc jet and also ion thruster. Today we will be discussing about electromagnetic thruster. Let us look at the basic principle which already we have discussed. When this ionized gas, that is plasma, and plasma contains everything like ion, electron and neutron, all the things, and when it is passing through this, and there will be electrical field which is subjected, and there is also the magnetic field. In this case, this ionized gas is accelerated using both the electrical field which is shown here E, this is EMF, electrical field, and the applied magnetic field is the B, which is shown here, and which are arranged orthogonally, that means perpendicular to each other. And this plasma is accelerated by the application of magnetic and electrical field along the direction, axial direction, as is shown here. This is F m, that is a magnetic force on the plasma is equal to dot cross product of J and B. J is your current density and B is your magnetic field, and it will be accelerated, unlike in the electrostatic thruster where only ions are being used, not others like electrons and neutrons and others of the plasma. That is the difference between electromagnetic and the electrostatic as such. And the thruster can be classified into various categories based on the type of magnetic fields and internal current and state of operations. And let us now classify electromagnetic thruster into broadly into two categories. One is steady, this is your steady categories, this is also steady categories, right, and this is a unsteady or a pulse mode. And these steady categories can be divided further into two categories. One is the self excited, that means in this case the magnetic field will be self excited, and this we call self excited magnetoplasma dynamics. And other case, the magnetic field is applied externally to enhance its performance, and that we call applied field magnetic plasma dynamics. And beside this, the Hall effect will be there, which is a current which will be produced along the electric field, and when it is interacting with the magnetic field, then that will give Hall. However, we will be discussing about magnetoplasma dynamic thruster. And beside this, the unsteady, what we call pulse plasma thruster, which will be basically changing with respect to time. That means, you will be applying this energy in a pulse mode than that of the steady mode or unpulse mode. So, this also we will be discussing. In this case, the temperature greater than 5000 generally will be occurring, and exit velocity we can get something 20,000 to 50,000 meter per second, sometimes may be lower also. The efficiency of such kind of electromagnetic thruster will be in the range of 30 to 40%, and it can produce neutral exhaust as plasma contain both positive and negative ions, unlike in case of ion thrusters. And one can also get high thrust per unit area, that is something 10 to 100 times as compared to the ion thruster, because all the particles of the plasma are being utilized in case of electromagnetic thruster. So, let us look at magnetoplasma dynamic thruster, and we will be looking at a schematic of a typical self excited magnetoplasma dynamic thruster shown here. In this case, the high voltage or the electrical power is being utilized here, which is being connected to the cathode and anode. Keep in mind, this cathode anode is has to be the gap. This is known as the gap. Gaps should be maintained properly. It is a little bit exaggerated here, and the propellant gases is passing through this, and where the magnetic field is being generated due to this electric field, and that will be really utilized to accelerate the plasma. And generally the gaseous propellant through this coaxial chamber, this is your coaxial chamber, over the cathode get ionized by passing through an intense azimuthally uniform electric arc field, and as a result there will be arc which will be produced, particularly the gap between the anode and cathode, and this generally towards the tip, because this gap will be little lower, and then so that this arc will be ionizing this and producing the plasma, and also and this accelerating propellant passing through the heart produces plasma just beyond this its tip, and subsequently it get expanded along to produce the desired thrust, and that is your J into this one, that is your exhaust, the magnetic field, and this is the current density. And of course, at the low current level, the ohmic and near electrode voltage losses are to be more, hence the efficiency will be low. However, at high current it really works very well, and then for that one has to use that, right. And as this ohmic and near electrode voltages losses will be more, therefore, that is the reason why the power level of self excited magnetoplasma dynamic thruster is restricted to only 100 kilowatt. So, that is the limitation of this kind of thruster. In order to augment this further, what is being done is basically you use the applied magnetic field, which will be basically accelerating the plasma further, such that you will get the higher thrust or the velocity. And as the magnetic field is applied externally, it will be having higher thrust density, and efficiency will be also higher. And this kind of thrusters for novel gases can have a maximum efficiency of 35% even at a megawatt power level. And both types of magnetoplasma dynamic thruster will have a higher level of cathode erosion. That is the biggest problem, because you are using a very high voltage over here, and therefore, cathode erosion is the one problem. And the problem of cathode erosion can be avoided using this kind of thruster in a pulse mode. So, let us look at now a pulse mode, plasma thruster, and the schematic of a pulse plasma thruster is shown here. And you can see that in this case this is your cathode and this is your anode, which is supplied to the power supply and a pulse generator, and this pulse generator will be supplying the power to this cathode and anode in a pulse mode that can be controlled according to the design. And then when this anode and cathode are subjected to pulse high voltage, then what will happen? A spark is produced, and this spark will be really penetrating into the solid propellant Teflon. This is not your gaseous propellant, solid propellant, and that will be eroding these solid propellants, and this will be producing the plasma, and that will be accelerated. Keep in mind, the solid propellant Teflon which will be getting consumed has to be fed with the help of propellant feed spring, which is shown here. And as I told earlier, that in this kind of thruster, a pulse flow of plasma in the order of 10 millisecond can be produced by using a rapid electric discharge across the anode and cathode, such that the solid propellant will be getting consumed and producing plasma, unlike in steady magneto plasma dynamic thruster. And in this case, very low voltage as compared to the magnetoplasma dynamics is being used, that is 1 to 2 kilovolts across the electrode, and the as I mentioned earlier, the Teflon gets degraded into carbon and fluorine atoms and ions in the pulse form and producing the basically the plasma, and this can provide the specific impulse in the range of something 1000 to 1500 second. Of course, the specific impulse is little low, particularly at higher power level, and it can be operated over a wide range of mean power or the thrust by simply varying the repetition rate of the pulse, and hence is used for precise orbital or attitude control applications. Keep in mind that this is being used very much because of fact that this electrode erosion due to the high voltage and the power level will not be really much, as erosion rate between the cathode and anode in case of plasma thruster is being reduced drastically due to the pulse mode what is being used in this case, and hence it is used in real applications, and hence these are being used in early LES-6 satellite, US Navy's transportation incentive program systems and NOVA spacecrafts. And it is still preferred for relatively lightweight propulsion applications due to its higher reliability and precise control capability. So, that is why this is really being preferred and can be used for several applications as I have mentioned just now. In case of nuclear rocket engine, various nuclear energy sources are being utilized. Those are fission energy release and radioactive isotope decay and fusion energy release, but we will be discussing about basically fission of the nuclear material, and the nuclear fuel what is being used in case of nuclear rocket engine is enriched uranium, that is U-233 or the plutonium P-239. Keep in mind that generally U-233 is produced from thorium-232 by neutron capture, hence does not require any further enrichment. That is why it can be used very much for the nuclear rocket engine. Let us look at a typical solid core fission nuclear rocket engine. Of course, there is a other model also for fission nuclear reactor, and schematic is shown here. If you can look at this, looks to be similar to the chemical rocket engine. That means, it is having the thrust chamber and it is having a nozzle, and the liquid propellant, particularly the hydrogen is being preferred, is passing through this, and then with the help of valve, and it will be going through the cooling jacket. This is your cooling jacket, the passing through that, it will be taking out the heat from the nozzle and also the thrust chamber. And inside this thrust chamber, the nuclear fission reactor is being placed, which is having a nuclear reactor core, having the fuel, and there will be also a control rod is being used to control that the nuclear reaction rate, and there is a reflector which will be helpful in not allowing the radiation to go out, and so also the shield which will be helpful. And this propellant, when it passing through, it will come in contact with this nuclear bed, and then the heat generated due to the nuclear fission reaction will be passing through this to the propellant, and as a result the temperature and pressure of this propellant will be increased, and that will be expanded in the CD nozzle to produce the thrust. So, this is similar to that of your chemical rocket engine. Only difference is that in this case the nuclear energy being utilized and in place of chemical energy. And nuclear fission engines have a higher thrust level in the range of 30 to 989 kilonewtons, and velocity, exit velocity, that is your VE, can be produced in the range of 6000 to 10,000 meter per second, and specific impulse as high as 1000 seconds can be achieved at least for a shorter duration period, which can be used for manned planetary exploratory missions. Of course, till now nobody has used these nuclear rocket engines, but maybe in future it can be utilized. And there are several research are going on across the globe, and I hope one day this will be fructified. Let us look at the solar rocket engine. There are various kinds of solar rocket engines people have conceived. One simple way of doing is that your photovoltaic cells, and which is being used, but it is having limitation of this, having a very large surface area, and also the structure has to be important, and it will be little heavy, and its efficiency is being very low. And of course, this can be utilized in the space where there will not be any hindrance to the solar radiations, and that we will not be discussing. There is also solar cell, which we had mentioned. There will be photons from the solar radiation will be imparted into cell, and then this will be can be utilized to produce the thrust. That also will not be discussing over here. And let us look at a typical solar heating rocket engines, which is similar to that of the your chemical rocket engines. Only thing is that instead of chemical energy being utilized, in this case solar energy in the is utilized to heat the propellant, and that will be expanded in a nozzle to produce thrust. Let us look at a typical solar heating rocket engines, and if look at, this is your propellant pressurized gas, which is used to pressurize this hydrogen tank, and with the help of valve the propellant can be passing through this your heat receiver. This is your heat receiver, and which will be receiving the heat basically from the solar radiation with the help of parabolic reflector. This parabolic reflector can be made of either the parabolic mirror or the Fresnel lenses. If you remember that Fresnel lenses have a very distinctive stepped surface that bends the light and concentrates the light into a super powerful beam into this heat receiver or the heat exchanger, in which the heat will be transferred from this rays to the propellant, and this will be this high temperature high pressure propellant will be going through this thrust chamber, and then it has to be expanded in a nozzle, and so that you can get the thrust, right. So, the gas temperature in this solar heating rocket engine can go up to as high as 2200 degrees Celsius. Of course, one can go a little further depending on the material, depending on the kind of propellants being used, and thrust level in the range of 1 to 10 Newton with 3 times higher performance level as compared to the chemical rocket engine can be achieved, but the level of the thrust is quite low as compared to the chemical rocket engine. And it can only be deployed in a space as it can not experience the atmospheric drag, being large in size and lighter weight. So, as I mentioned earlier, this is the reason why it cannot be used on the Earth surface or any other planet, and it poses the problem of hydrogen propellants like your storage problems and other kinds of problem, but however, hydrogen is being preferred over here due to its thermal diffusibility being higher. So, therefore, it is being utilized for in case of solar heating rocket engines. Now, let us look at another rocket engines, that is known as Hall effect thruster. In this case of Hall effect thruster, let us understand what is that. For that we will have to look at the field what we are considering. This is the propellant which will be passing through, it is having a axial electric field and transverse electric field, right, and it is subjected to, if you look at the electric field where it is subjected E, and then it is also perpendicular to the magnetic field which is coming, there will be a current which is passing through that is known as Hall current, and the AF will be a product of this J into B. That means, in other words, when a conductor with a current flowing in one direction is introduced perpendicular to the magnetic field, this is your perpendicular, like current is passing through this, right, and then this is your magnetic field perpendicular. A voltage is produced at the right angle in this direction to the current path, which is known as the Hall effect. So, this is your Hall current jet, and this Hall effect is being utilized to accelerate the propellant so that you will get. And this interaction of this Hall current with the magnetic field produces an axial force along with this direction, this is your axial direction x, and that accelerates the plasma. This is the basic principle of Hall effect thruster. So, let us look at a typical Hall effect thrusters, in which case there is a anode and there is also cathode, the high voltage is being utilized, and this is the annular place through which the propellant is passing. So, generally xenon is being preferred as I had mentioned earlier, and this is your magnetic field which will be acting over here, and this is your electrical field, and this is your magnetic field which is acting over here. And in this case, when the propellant is passing through, then it will be plasma will be created and accelerating. In order to enhance this one, then one can also the pass through in the swirling form, and swirling flow of the electron generated by the magnetic field and electric field creates a Hall effect that accelerates the plasma, because these two fields are there. As a result, the propellant will be moving in a swirling manner like this. So, that will be helpful in basically accelerating the plasma, and that is why it is being utilized. Of course, like electron and ions are produced, and there is no nozzle in this case as in the chemical or the electrothermal rocket engines. So, a very high exit velocity one can achieve, that is in the range of 15,000 to 25,000 with the voltage in the range of 200 to 500 volt. That is the beauty of this Hall effect thruster as compared to other electromagnetic thrusters. The flow rate of propellant is between 2 to 10 milligram per second, which is very, very low. The overall efficiency lies between the 50 to 60% as the electron do not contribute the generation of the thrust, and higher thrust per unit area is around 10 times as compared to the electrostatic thruster due to absence of space charge limitation, because the space charge limitation is really which hinders the performance of the electrostatic thruster, and therefore, Hall effect thruster is being preferred over others. And let us summarize what we have learnt in this lecture. In this lecture, we looked at various kinds of the non-chemical rocket engine, most of which can be utilized only in the space where the drag and the gravitational effect will not be there, and where the thrust requirement will be very low, whereas the specific impulse developed by this non-chemical rocket engine can be utilized to have a long duration operation. In this lecture, basically we have looked at mostly the chemical rocket engine, and we also have a now feel for the non-chemical rocket engines, and I have covered most of the things, but this is being an introductory lecture. I have covered in a very simple manner and without really involving too much of analysis, and I hope and that you might have enjoyed this course. But if you are interested to know more about non-chemical rocket engine, you can refer my book or any other books on this. There is a specialized book on the non-chemical rocket engines that you can read, and I wish and hope that you might have enjoyed this course. Wish you best of luck for your future endeavor, and do something for safeguarding our culture and tradition, our great motherland, that is Mother India. Thank you very much.